Welcome to EPG Pachala. I am Dr. Venusatini from the Department of Philosophy, University of Hyderabad. This is Logic 1 and the module on which I'll be talking today is Basics of Set Theory. The course is written by Dr. Mamata Bandyopadhyay. Well, we'll begin with a rough definition of set. Not definition in the technical term, but more like a description. So what is a set? Normally we can define set as a collection or collection of things or group, or sometimes we say it's a class. Simply put, when there are things and we need to collect them, we say it's a set of things or collection of things. Now this collection need not be systematic, in the sense that I can talk about collection of a number along with human beings and name of the cities. I can also talk about systematic collection, like collection of all plants or collection of some sort of animals like tigers, or even collection of Indians. So that is a rough definition of collection. Now whenever we talk about collection, we also have to talk about collection of, that is members. So when we talk about set, we also think about membership. So sometimes membership is also defined in terms of belonging to, that a member or an entity belongs to some class or member or a set. Whenever we talk about a collection of number, then inside that collection you will find numbers. In that set you will not find other things like box or table, chair. It is about numbers. And so if I say number 10, 10 is a member or of natural number, or sometimes positive integer numbers. It's a collection of numbers. Now to represent this set, we have given a symbol, and the symbol is represented by curly brackets or sometimes called braces. As far as membership goes, we have a symbol, and it's a Greek symbol called epsilon. It is just like E. Let us see on the board what is E. And then when we say that something is a member of something, then we represent by saying that let us say A is a member of a collection called B. So now we have two notions here, a set and membership. Each set normally is given a name. So name of a set can be written in the form of A, B, C, D, etc. And within set there will be members. So let us take for example a set A, and it has members 1, 2, 3. How do we represent this? Let us look at the screen. So suppose we have a set, then all these 1, 2, 3 will be separated by commas and then closed by braces or so-called curly brackets. We can mention some properties of this relationship between a set and its members. Now this membership is uniquely between entities and the class, the set. Now between given two sets A and B, A cannot be a member of B, and also B cannot be a member of A. And if A and B are sets, or if A is a set of B, then B cannot be a member of A. Or given another situation, if A is a member of B, then and if B is a member of another set C, it does not necessarily follow that the set A is a member of the set C. We have to take care of this, otherwise it results in some kind of paradox, which we will not do it here, but these are some of the things that we need to keep in mind. Going on, we can talk about now relation of sets. I mean, given set A, set B, can we define the relation between these two sets? In the first place, the kind of relationship that we are talking about is between a member and the collection set. Now the next is relation between sets A and B. So this is defined in terms of one subset or inclusion of set. Suppose we have a set A and then we have a set B. We can define one type of relationship and it is called subset. When is set A subset of another set B? It is technically defined like this. Let us look at the screen. When A and B are sets such that all the members of A are members of B, A is called a subset of B. Symbolically put, it is A something C underline and then B. And more technically defined in terms of logical language, A is a subset of B if and only if, represented by double arrow, for all values of x, if x is a member of A, then x is a member of B. Let us say we have a set A and it has a member 1, and let us say another set 2, set B, it has 1 and 2 as its members. Then we are saying for all values of x, if x is a member of A, that means 1 is a member of A. It is also a member of B. That means 1 also ought to be a member of B, in which case A is a subset of B. Here look, we are saying all members of A, and in A we have only 1. That's why 1. If there are more members, then we have to specify one by one that 1 is a member of A and 1 is also a member of B. 2 is a member of A and 2 is also a member of B. Likewise, for all the members in set A, we have to specify one by one and then show that they are also members of B. But the reverse is not true. We need not show that all the members of B are also a member of A. We need not show like that. Then from here, we can also develop into a special type of subset relation, and we call them proper subset. Now, here proper subset is such that all the members of A should be a member of a set B, but proper in the sense that A cannot have exact number of members as that of B. In other words, B should have at least one member more than the set A. Comparing with the first definition of subset, in the subset, all members of A can be members of B, and then the numbers may be equal. All the members of A are also members of B, and B need not have any extra members. But here in the definition of proper subset, B must have one member which is not in A, while at the same time containing all the members of A. So let us look at this example. A is a proper subset of B even only if for all values of x, x is a member of A and x is also a member of B and A is not identical with B. How do we show that it is not identical with B is that there must be one element in B which is not there as an element of A, which give us the idea of non-equality. So given this, let us say A has one element 1 and B has two elements 1 and 2. So there we can say that 1 is a proper subset of B, which is having 1 as an element of A is a proper subset of B having two elements 1 and 2. So given the we can also define more proper subsets, like given the set B having 1 and 2 as its member, 2 is also a proper subset of B. But if 1 and 2 are members of A and also B is having two members 1 and 2, we cannot say that A is a proper subset of B, because in this case they will become equal or identical. So we go on to the next one. This idea of equality gives an interesting principle of set theory, which we call it principle of identity, or sometimes the principle of extensionality for sets. So what is this principle? we say that two sets A and B are identical if and only if represented by arrow. For all x, x is a member of A if and only if x is also a member of B. In other words, put it differently, A is a subset of B and B is also a subset of A, which we have seen before. So when that happens, that is A is a subset of B, B is also a subset of A, then we call them identity of sets. They are identical sets. Now from here we go on to talk about another very unique set. Unique set in the sense that they have no members. Often set is defined by the members. But suppose we cannot find any member, can we talk about such a set? We say in set theory, yes, there exists such a set which has no member. Now let me give an example. A set of all mountains taller than Mount Everest. There is no such set. I can talk about a collection of all entities such that they are square and also triangle. You can never have such a figure, both square and triangle. So that set is empty, and which is represented by a kind of inverted V. In Greek it is called lambda. Sometimes they use another Greek symbol phi. So this is represented by either lambda or phi. That means this set is unique, and technically we can define this as follows. Let us see at the screen. For all x, it is not the case that x is a member of lambda. That is a set. Or put it differently, for all x or for any x, it is not the case that x is a member of lambda. That lambda is a name of a particular set. Now there are some unique properties about this set. That is, empty set is a subset of every other set, including itself. That means if you can think of any set, any collection, automatically by default empty set becomes a subset of this. How? I mean, give reason. First thing, to say that it is not a subset, we must be able to give, or rather show, by saying that here in set B there is one element and it is not there in A. To say that this is not a subset of A is not a subset of B, but by definition empty set is that it has no member. So then we cannot produce a member saying that this is a member of A, which is empty, and then it is also a member of B. So vacuously, in other words, we cannot demonstrate that here is an element which is a member of empty set, and then it is also a member of another set called B, which has some element. We cannot really do that. So if you look at certain truth conditions of material implication, you will understand better. For example, in material implication, if we have a statement like if A then B. Now if antecedent, which is A, is false, then by default or vacuously the whole sentence becomes true, irrespective of whatever is the truth value of the consequent. So here, because we know that if a set A is empty, saying that that empty set as a member is already a false sentence claiming. So that means if part, if is false, so by default the whole sentence becomes true. That's why we say that empty set is a subset of every other set, not because we can demonstrate, but because we cannot falsify it. Now the other property of empty set is this, that there can be one and only one empty set, or there is exactly one empty set. Let us say, for the sake of experiment or discussion, say there are two empty sets A and B. Now by definition we know that A is a subset of B. Why? Because empty set is a subset of every set. Now we change the relation. Can B be a subset of A? Now we know that B is also empty. So by definition it goes, B is a subset of A. Now, our definition of identity of sets or principle of extensionality says that if two sets A and B are subsets of each other, they are equal. Now then I can show that A is identical with B. Now you can even think of another set, empty set C. But you define B is a subset of C and C is also a subset of B. Now if that holds, then B and C are equal. Now we know that A is a subset of B and A and B are identical. So then from there we can go on to infer that A is also identical with C, because we have already shown that B and C are identical. We can keep on adding different kinds of empty set, but still then by applying certain rules of inference we can show that ultimately all empty sets are equal or identical. Now we have talked about two different kinds of relation in set theory. One is membership, the other is relationship that holds between sets. Now we move on to the next level, which is operation of sets. Suppose we have two sets A and B and they are non-empty, in that there are members. Can we define some operation in such a way that we get a new set? And there are different ways to define operation on these two given sets. We'll begin with one, and that is called operation of intersection. That is intersection between two sets. Given any two sets A and B, we say that A intersection B, even only if whatever is a member of A is also a member of B. Now, how is that different from subset relation? We can look here. It is not same in the sense there may be a member of A which are not a member of B. There may be a member of B which are not a member of A, but there are some common elements. We are thinking of common elements. So in order for the intersection to be possible, we say A intersection B, even only if the member are such that it is both member of A and member of B. That is how it is technically defined. So now let us look at the example. Suppose we have a set A having 1, 2, 3, 4. And another set B having members like 2, 4, 6, 8. Now keep in mind that every time you write numbers or you list the elements, they should be separated by commas. Otherwise there will be confusion. Here when we define intersection of A and B, what are the common elements between A and B? We look and we see that 2 is a member of A and 2 is also a member of B. 4 is a member of A and 4 is also a member of B. So intersection of A and B will give us another set 2 and 4. Now keep in mind that we are doing operation of sets. So we are generating new sets from the given sets. So don't confuse with membership or any other kind of relation between sets. Like when we talk about relation of subsets, we are not generating new sets. But in this case, every time we define an operation on sets, we are generating new sets. Now given two sets A and B, we can define another operation of sets and we call it union. How is the union of sets to be defined? By saying that for any value of x or for any x, if it so happens that x is either a member of A or x is either a member of B, then we say it's a union of set A and set B. So given the set, let us look at the screen. Given a set A 1, 5, 7 and B with elements 5, 6, 7, how do we define the operation of union? Simple, just list down all the members which are in A and also in B. That means union either, so that means 1 is a member of A, qualifies. 5 is also a member of A and also B, it qualifies. 6 is from B, so it is true. 7 is from B, it is true. So that means for something to be a member of union, it need not be a member of both the sets. It satisfies the condition if it only is a member of one of the sets. That's why either or. Now we can have more sets operation, and the next one is difference of sets. For any two sets A and B, A difference B, symbolically put A kind of minus or tilde B, is the set consisting of the members which belong to A but not to B. Technically put, for any x or for all values of x, x is a member of A difference B if and only if x is a member of A and not a member of B. Now that means think of a situation such that we want all the Indians but not women. That means we are doing some kind of subtraction. Now, Indians minus women will give some kind of difference of set. In the sense, all Indians who are not women will give us male Indians. Likewise, let us show by first some numbers. Let us look at the screen. If we have a set A and set A has members like 1, 2, 3, 4, 5 and B has set 2, 5, 7, then we can define an operation on these two sets. A difference B is equal to, here on the right hand side we are making new sets. Remember, keep in mind that 1, 2, 3, 4, 5 minus set 2, 5, 7, which will give us this new set 1, 3, 4. That means whatever is there in B has been subtracted, as a result of which we get 1, 3, 4. Or we can also define a difference of set from B to A, B difference A, in which case we have to write all the members of B which are not members of A. So as a result of which we get only 7, because the other two 5 and 7 are members of A, therefore disqualified. So at the end we get 7 as the only member. Now there can be more complex relationship between sets and some others, and then set should be able to help us to define relationship of all kinds. And here is where we want to introduce a kind of a unique relationship called complementary of sets. Something like difference of set, but not really difference of set, because here we are no longer comparing one set with another set, which member is there, which member is not there, but in terms of something very large. Let us say set of all sets, or in set theory we call them universe of discourse. So complement of set is always defined in terms of the universe of discourse. For example, in sociology we can talk about all sets of human beings. So the human beings becomes the universe of discourse. In botany we can talk about set of all plants, that is our universe. Likewise, in mathematics, let us say numbers constitute the universe of discourse. So when we have such a universe of discourse, and within that universe we want to explicitly point out some set, then when we say complement set A, means all those members which are not in A, but still they are members of the universe of discourse. So let us look at some example. Let us say that universe of discourse can be represented by V or some U, but conventionally or conveniently here we have introduced V. This universe of discourse is, as I said, can be set of different sets. Now let us say Indians is our universe of discourse. In this universe of discourse we can have different sets, like set of all Telugus, set of all Malayalis, let us say set of all Punjabis, and things like that, because the universe of discourse is Indians. And let us say the name of the set A. Set A is the set of all Telugus. When I define complement set, that is complement set of A, what are the members of the complement set of A? That means all the members of the universe. That means Punjabis, Malayalis, and whatever classes of Indians that we know of, can be listed minus the Telugus. So complement set is defined like that: members of the universe of this course, but not the set about which you are talking. Now suppose we have set V having 2, 4, 6 as members, set A has 2, 4 as its members, and set B has 4, 6 as its members. So what is a complement set of A? Then it is universe of this course minus A. That means all members of the universe of this course but not A. Now given these sets A, B, we can think of the definition like this. That is, complement A will give us 2, 4, 6 minus 2, 4, because 2, 4 are members of A and we don't want them. So which will ultimately give us 6. Now when we talk about complement of B, think of the universe V. Here it is, V is 2, 4, 6. Now V minus B, that is 2, 4, 6 minus 4, 6, and we get 2. Suppose now here we have fixed the universe of this course as finite with few entities. So that means the whole subject matter in our universe of this course here is just 3 numbers, 2, 4 and 6, and in relation to this we are defining complement set. Now we move on to next relations, which is still more complicated. So far we have talked about different relations. Keep in mind, we will be going to the next level of relation, and that relation will be between members. Now first was between member and set, second was between two sets. Operation of set is about generating new sets given some sets. Now the relation about which we are going to take a look is, given any set, what is the relation that holds between members inside the set. So let us say, take for example a person who is a teacher and a person who is a student. That means given a classroom, there will be teachers and student. So how is one person related to the other? If A, B, C are there, suppose A is a teacher, then B is a student. The relation is one of teacher-student relationship. But B and C are students, so the relationship is one of students, not a teacher-student relationship. So in other words, given any collection, we are able to define relationship between the members. Generally, given any set, let us say a set A with 1, 2, 3 as its members, it doesn't really matter whether you put 3, 2, 1 or 1, 2, 3 or 2, 3, 1. Sequence doesn't really matter. But now when we are talking about relation of members within a set, then ordering becomes very important. And it is in this sense that we are going to talk about this membership relationship between or in a set. And to begin with, we will be talking basically of only couples or ordered pairs, though it is possible to talk about ternary relation or triples or quadruples. We can define so many kind of relationship, but here in our class we will be only talking about ordered pairs or ordered couples. So that means they will be represented by not the usual curly brackets or braces, but by round bracket, which we can notice at the board. An ordered couple is two elements in a fixed order. X, Y is an ordered couple whose first member is X and second member is Y. In the case of ordered couples, the order of the element is of primary importance. That means given any ordered pair or ordered couples represented by a round bracket and then first element X, Y. The idea of ordering is that X, if it is a first element, it should never be confused with the second element Y. So the X will be treated as first element and y will be treated as the second member of the element. In other words, let us say x is a teacher and y is a student. If we change the sequence, x will no longer be a teacher of y. That means y being a student, if we put y first and x teacher, x is a student later, then the relationship is going to be affected. So that's why ordering is very important here. But of course, we can define identity or equality of ordered pairs or ordered couples, and that is two ordered couples, for example x, y, and another ordered couple u, v are identical only in one circumstance or condition, that is just in case first element of the ordered pairs are equal, that is x is equal to u, and also the second element of both the ordered pairs are equal, y is equal to v. Now see, x is the first element of the first ordered pair and u is the first element of the second ordered pair. Likewise, y is the second one and v is the second one, in which case we can say that x, y is equal to u, v. There is a very special technique to define all possible relations that can hold between members in a given set, and that we do by a Cartesian product. How should we understand Cartesian product? Then the Cartesian product is always defined on non-empty set. Now given two sets A and B, we can define Cartesian product A into B. The usual into multiplication sign comes between A and B in such a way that x is a member of A and y is a member of B. That means all the first element of the ordered pair belongs to the set A, and the second element of the ordered pair will be supplied by the set B. Suppose we have a set A and B. Let us look at the screen. If A has three members 1, 2, 5 and B two members 2 and 5, then we can define Cartesian product of A into B. That means Cartesian product, remember, is also a kind of set operation in that we are generating new sets. Now A into B, on the right hand side we have a big set. So all the first, that means A into B is a collection of ordered pairs where all the first element of the ordered pair comes from set A and the second element of the ordered pair comes from set B. So given A into B, we have ordered pairs 1, 2, 1 and 5, 2 and 2, 2 and 5, 5, 2, and then 5, 5. We have 1, 2, 3, 4, 5, 6 members. We can also define Cartesian product from B to A or B into A. In such a case, now all the members, all the first element of the ordered pair is supplied from the set B, and the second members are coming from the set A. So we have 2, 1, 2, 2, 2, 5, 5, 1, 5, 2, 5, 5. Given any set, we can analyze this in terms of specific terminologies. That means domain of the relation R, knowing that R is actually a Cartesian product of sets A into B, and then another concept called codomain or counter domain. And all the members of the sets, let us say A and B, taken together are called field. And whatever is the first element of any relation in ordered pair will be called domain, and whatever is there as the second member of ordered pair will be supplied by the codomain or counter domain. Let us look at the board screen for this. The domain of a relation R can be explained like this: D within bracket R is the set of all x such that for some y in x, y is a member of R when, for example, R is such that it is a set with three members 1, 2, 2, 3, 3, 4, the domain of R will be understood as a collection 1, 2, 3. Then the counter domain of a relation R. Given any relation, we can have a set called counter domain. Then it is expressed by C within bracket R is the set of all Y such that for some element of X, XY is element of R. That is, given any relation R, then it's a collection of ordered pairs we know. So 1, 2, 2, 3, 3, 4. Codomain of their relation is a set with members 2, 3, 4. Notice that all 2, 3, 4 are the second element of the ordered pair. And as I said, the field of a relationship is a union of domain and codomain. So given this field, rather relation such that 1, 2, 2, 3, 3, 4, we can have the field of R, which is a union of D, means domain and codomain. The set that we will get is 1, 2, 3, 4. That is 1, 2, 3 being the set of domain and 2, 3, 4 being the set of codomain. We can generate the field of this relationship, which are actually the union of these two 1, 2, 3, 4. Why are we doing this basics of set theory? Basically, set theory is an attempt to articulate clearly and simply basic intuitions about the structure of thought or relations. So here we have seen that we can talk about relation of different types between member and set, between two sets, and given two sets, what kind of operation we can do to generate new sets, and also given two sets, how are we to understand the relation between the members of a set, that is by doing Cartesian product. So this way of stating and explicitly or systematically specifying relation will help us to think logically, that means think with clarity and systematicity. In this sense, set theory is a tool for doing modern symbolic logic.